congratulate him after his talk. And now we have Yufeng's certificate. Yufeng did his undergraduate studies at the University of Science and Technology in China with a major in probability and statistics. He's currently working under the supervision of Zhao Ran on non-convex optimization, machine learning, and reinforcement learning. And their goal is to develop provably efficient learning algorithms for decision-making. Okay, so congratulations to both Linchuan and Yufeng.
Thank you.
Now, has George joined? No. All right. So let's go ahead with your presentation then, Linchuan.
Okay. Thanks for the introduction. Let me share the screen now. Can everyone see my screen now?
Yes, yes, we can see it.
Okay, cool. So it's a great honor for me to be awarded the Nemhauser Best Paper Prize, and today I'm going to present my work on the classification of constrained nonlinear optimization problems with indicator variable. This is a joint work with my two other collaborators, Anders Gomez and also Cindy Kudikibasi from our department. So our motivations come from the very classic example in regression analysis, which is so-called best subset selection problem, where we have a data matrix and we have response vector, and we try to fit a linear regression model with the additional constraint saying that we're only allowed to select at most key features. This problem, although it looks very simple, but it has very good explanatory power, especially in the high-dimensional setting, where we have the number of features significantly greater than the number of observations. But the problem is that the best subset selection problem, it has a very strong combinatorial features, meaning it has been considered as an intractable problem by the statistics community.
Let me interrupt you for a moment here, Linchuan. George Nemhauser has joined us as far as I can see.
Okay.
Hello, George.
Hi, Jorge. How are you? Can you hear me?
Great that you can join us here.
Well, I'm glad to see some good work being done.
We appreciate the fact that yeah, you never forgotten that you had a good education here at Northwestern, and you've been supporting us for many years.
Thank you. It's good to see you, Jorge.
All right.
Yeah,
Thanks.
sorry to interrupt, but
no, that's good. Go ahead, Linchuan.
Okay. Okay. Yeah. This problem has been considered as intractable, meaning it is an entire problem. In the worst case, there is no polynomial algorithm to solve the best subset selection problem. So we can actually formulate this problem in a more general way using the mixed integer programming language. Actually, we can introduce the binary variable and model this kind of on and off relationship between Zi and beta I. So from this constraint, we can easily see that if Zi is 0, which it automatically implies the beta I is 0. This kind of on and off relationship has been studied quite well in the mixed integer society. And also we can also enforce arbitrary constraint on the other set of indicators, the I's. And as I said before, we can enforce arbitrary logical constraint that we want for feature selection to have. And I will also present you with some more exciting application of a particular use of such constraint. And there is from the mixed integer point of view, we can view the Lasso regression as a particular convex integration to the mixed integer problem. And in Lasso regression, we replace the L0 norm by its a convex envelope, which is the L1 norm, the sum of absolute value. And it has a very nice property. It actually induces sparsity in the fitted model, and it has pretty good generalization in high dimension. And there's quite a lot of literature in statistics about the Lasso regression. So actually, there are a bunch of other mixed integer formulations for the structural regression problem with sparsity. The first method is also well known in mixed integer society, which is called big M method, where we replace the original very complex constraint by the constraint saying that or beta has to be within plus and minus m times c interval of the constraint. So if Ci is 0, which also automatically forces the beta s to be 0, it's a quite I would say it's a quite traditional way of modeling this kind of on or constraint in mixed integer optimization. But there are several issues with that method. The first one is like a particular tight value of n is very critical for the strength of this formulation. And also, if we want to solve this mixed integer problem using the branch and cut solver, then the value of n has also have a very large impact on the solution time. But however, in the regression setting, there is no natural tight value that comes for free, and there are some researchers that consider a tight estimate for that big N value, but it's all under very strict conditions on the data matrix. Another parallel line of work used the so-called perspective formulation, and from the formulation you can see that the perspective formulation actually it replaced the separable L2 loss function by its corresponding perspective function, taking respect to the corresponding Ci variables. And it's also directly modeled the same problem. For example, if we let Ci to be 0, then to avoid class infinity, we have to make the corresponding beta I to be 0 as well. So that in that way, we attend the same modeling. So I would continue with more details about the perspective formulation. These ideas come from the simple one-dimensional quadratic case with indicator variable. So for example, in one dimension, if we have the epigraph of quadratic, one-dimensional quadratic, and then if we want to take the convex of the set R, actually this can be obtained by first replace the binary restriction by its continuous 0, 1 interval, and also we replace the quadratic function by its perspective function, which is the beta square divided by b. And there is a simple graphical illustration of that convex of, which you can see is the convex of R. Actually. So in our research, in our work, we take a step further. We consider a more general loss function because in machine learning, there's quite a lot of fancy nonlinear loss functions. So our work concerned with the general convex loss function. So suppose the objective function can be written as the sum of convex loss function plus L0 norm in the end, represented by the indicator variable. And we also consider arbitrary structure constraint on the binary variables. And in here, we assume xj convex loss function could be non-differentiable, and that our result will give a very good ideal formulation for that structure. So let's first begin with some application. So in the previous simulation, we add arbitrary constraint on the indicator variable. But what are the most examples for that constraint on the features? So let's consider a very simple example where in a regression setting, we add the pairwise interaction term. Like it's in the box, we have arbitrary pairwise xj times xi times xj, and we have corresponding coefficients on that interaction term as well. So there is a so-called strong hierarchical relationship among the features. So it says if we add an interaction term, if and only if we have included the corresponding main effect in this linear model. Not only does this kind of strong hierarchical relationship actually fits our common sense, but it has a very nice property in high dimensional statistics. Actually, it results in a more sparse but more interpretable model. And let's first look at the spread regression before we go into our general convex loss function case. Here we have the loss function, which is the sum of square, and we have the arbitrary constraint, say it's in Q. And let's first look at the more like a little bit easier convex epigraph. So which is the mixed integer epigraph on the square of a sum theta, which is rank 1 quadratic function. It is very representable because in sparse regression, the loss function is actually a sum of rank 1 quadratic function, and we pick a particular component function and see if we can convexify this mixed integer epigraph. Actually, we can get a very nice convex description in 2019 by Adam Kerr and Gomez. They provide a description for that convex code. And if we look at their description, actually this is obtained by first we convexify the binary indicator variable by its continuous 0-1 bound, and also we add at the end of this bracket, we have a term which is very similar to the perspective function of quadratic. Besides that, we in the denominator we have the summation over ci. So, and we will start with some intuition of that value equality and why it is give us ideal formulation for that convex. So, and use this idea, we can generalize to general convex rank 1 loss function. So let's first give some intuition about why the inequality that we saw in the convex description is actually a valid inequality. So we do this by case analysis. So first we consider if we have an indicator variable which is exactly 0, and then this by the constraint on and off constraint, it implies all the beta s at 0, and it becomes t greater or equal than 0, and our perspective function, the square of sum divided by summation over zi is 0 divided by 0, and we use the convention this number is also 0, and so this is the inequality holds. If it is not 0, so it is in the set of non-zero indicator variable, which means there has to be at least one index where there is a 1 there. So the summation over zi is greater than 1, and then we can easily see this fractional is less or equal than the square of sum. So that's all the intuition that we got for a simple quadratic case. But what are the lessons that we learned from the simple quadratic rank 1 function? So first of all, for that case, the unconstrained the set of constraint on indicators actually the set of all the binaries, two-dimensional binary variables. And we look at the denominator that appearing in the perspective function in last class is the summation over zi. And the interesting thing is that if we add the constraint summation over zi greater or equal than 1 together with the 0-1 bound, actually we recover the set of all the non-zero indicators, meaning there is convex call of all the non-zero indicator variables. So we say the summation zi greater or equal than 1 is a very strong separate inequality for 0 from the set of non-zero indicators. And in R3, we can actually visualize this effect. If we draw all the three-dimensional binaries, it forms a cube in R3. And if we look at the hyperplane 0-1 plus 3 plus 3 equals 1, it actually cuts off exactly cuts off the 0, the original at the corner of the cube. So now let's look at the general setting where we have a rank 1 convex loss function, and we have arbitrary constraint on C. We want to follow exactly the same reasoning that we did before. First, we look at the family of separating inequalities. We want, in a more formal sense, we want a set of inequality with 1 at the right-hand side, and together with this family of inequality, we are going to recover the convex of non-zero indicators once we have the convex of all the indicators. Together with this set of inequalities, we separate the zeros out from the convex form. And similarly, as before, previously, the strong value inequality that we got for rank 1 quadratic function is we take the perspective respect to the summation over zi, where summation over zi greater or equal than 1 is the strong separate inequalities. So similarly, we can also use this similar idea. We take the perspective function of the rank 1 loss function with the respect to the type transpose C, which is the left-hand side of the family of strong separate inequality that we have identified. And there are two questions. Are they actually valid inequalities? And actually our answer is yes. By using a technical lemma on the general perspective function, we can show they're actually valid inequalities. Are they enough to give us a convex description for general convex rank 1 loss function? And the answer is yes, but it needs some conditions. So the valid inequalities is come from a very nice and simple one-dimension technical lemma that we have proved. So it says if we have a convex loss function which has domain which has a finite value in the real line and it has 0 at 0, then there's an order on the perspective functions, meaning that if we have a smaller value on z, then we always get a bigger value for the perspective function. And this is use some property of the convex one-dimensional convex function, and it's not hard to prove. And therefore, if we look at the purest quadratic perspective function, and we can easily verify this property from the graph. So for that, in that graph, if we fix the value of x and then we decrease the value of z, it actually follows the line that I draw from the horizontal line that I draw in the graph. If we decrease the value of z, we actually go upwards in that graph. And that kind of phenomenon is also holds for arbitrary convex function. So the proof of the valid inequalities also follows the same logic. We separate the cases, like whether the z variable is 0 or it's not 0. If it's 0, then it follows exactly in the same way that we saw before. We have 0 divided by 0 in the function value, and so it's all 0. And if z is non-zero, then by the definition of our strong second inequality, type s of z is greater than 1, then using the order on the perspective function, we know this is less or equal than f evaluated at the summation over beta. And so this family of inequality that we propose is actually a valid inequality for our mixed integer f graph. And here let me present our main result is about the convex closure convex description for that mixed integer f graph with general rank 1 loss function and arbitrary indicator constraint. So this convex description, if f is convex and if we have some kind of connected structure on the indicator set that I will define later on, then we can get the closure of convex of dq. And by first we convex by the set of all the indicators, which is I denoted by convex of q. This can be represented as a bunch of linear inequality in the polyhedral analysis. And also we add this perspective-like inequality that I defined before. Together, we get a closure of convex form. Now, it's worth noting that our result is generalized all the previous convexification regarding mixed integer quadratic epigraph with indicator variables. And also, this kind of a result, it provides a general framework that can be used to very large number of applications. For example, in logistic regression, we have the logic function, which is also a rank 1 convex function, and also same for support vector machines. And also, as we write this paper, we noticed that there is actually several very interesting applications, like the unit commitment problem in energy, where we can also use our strengthening technique in the corresponding mixed integer optimization problem. Okay, so let's take a deeper look at what I mean by Q is connected. So first, we define a graph where the nodes that are all the indices from ICP, where it represents all the indices of the continuous variable. And we create at ing if and only if there exists an indicator variable that has 1 at both indices I and j. So in that sense, we get what we call an indicator graph. And we say the Q is connected if and only if the corresponding graph G of Q is connected in the graphic sense. And like we can look at a simple example where we have a 3-dimensional binary set and we force the restriction that we can take at most 2 of the indicators to be non-zero. And this actually results in a fully connected, complete graph in 3 nodes. So for example, nodes 1 and node 3 are connected because we have 1 and 0 in the set of Q, and also similarly 2 and 3 and 1 and 3 are connected. Okay. So the proof of our main result is based on a very fundamental, and I think that one of the most important result in convex analysis, which is the so-called support function. So for our arbitrary closed and convex set C, we define the support function as the supremum of all the inner product of A and with arbitrary x in C. So that support function, there is a nice result in convex analysis, saying that actually the support function is uniquely identify all the closed convex sets. In the sense, if the two closed convex sets they have the same support function, then we know they are identical. So using this idea, so to prove our convex closure of convex description, we just need to consider linear programming first over the mixed integer epigraph C of Q, and we consider another mixed linear optimization problem over our proposed convex representation, which is Y. And we show that they attain the same optimal value, or they are unbounded at the same time. So put it in another word, we showed the 2 sets, the closure of C of Q and Y, they have the same support function. And in that way, we showed they are identical. Okay, so our result actually contains several very interesting applications. The first application is the case sparsity constraint. So it asks the constraint saying the summation over Ji is less than K, meaning we can only take K of the features. And that's the best of the case of the selection problem. And for that Q, like we can get a very simple strong sequence inequalities, and it turned out to be the only one that we need to get a closure of convex description, which is the sum over Gi greater than 1. And by using our general result, just plug in this sequence inequality into the perspective function, and then relax the binary constraint, then we get the closure of convex. That's how our general result tells us. And similarly, we can also derive the closure of convex for the strong hierarchy constraint. And remember, the strong hierarchy constraint is saying that there is a particular features. If we select that feature, it implies we select a bunch of others. And that kind of logical relationship can be captured using the constraint saying like CP is greater than all the other Gi in some Q. And there is also a very nice strong sequence inequality for the 0 indicators for that particular set of indicators, which is summation over Gi over P, and then subtract P minus 1 times P greater than 1. And based on that sequence inequality, using our general framework, we did get a closure of convex of this mixed integer epigraph. And also we also independently consider a separable loss function, where the loss function, rather than being rank 1, is actually decomposed into separable variables, where we can represent it as sum of over Fi of beta i's. And for that simpler case, we also derive the convex description for that mixed integer epigraph under arbitrary constraint on Q. So that closure of convex description is very simple. It can be obtained by just replacing each component function by its corresponding perspective function taking respect to Gi. And also we independently reconvexify the set of indicators, and that gives us a closure of convex. So a nice interesting application is that sparsity logistic regression. This problem is not considered by any kind of mixed integer optimization person. So in sparsity logistic regression, we have our loss function as a sum of logistic loss function, and we also using the Z variable to model the binary, to model the feature selection. And note that this function is actually way more complicated than the simple projective loss function, and it's non-separable. It's rank 1, and there is no previous classification result stated. look at particular this example. And but actually all results can be used in that particular case because it falls into the category of one-to-one loss function. And by using our general mean result, we can get a tractable cognitive simulation of the sparse logistical regression problem. So in our numerical experiment, we also consider the least square regression with strong active constraint on the pairwise interaction. So in this problem, we add all the pairwise interaction term xi times xj, and we make a coefficient for that term as well, and we enforce the strong character relationship, meaning if Cij is 1, then automatically implies all the Gi and Zj are 1. And we formulate this problem in this way. And then we compare our relaxation, or convex of the relaxation that we got from our convex substitution with 2 others existing relaxation. The first one is use the original idea of the perspective simulation, whereas if we can separate a separable quadratic term from the big quadratic term in the regression problem, and then we take their perspective function accordingly, then we get reformulation. So in 2015, by Jeff and Dong, they provide a SPT formulation to get the optimal perspective relaxation. So by optimal, I mean like there are a bunch of ways that one can extract the separable quadratic term from a big quadratic function, but which decomposition gives us the highest lower bound. So there is a ICT formulation to that problem. And I didn't mention, I didn't give the full details, but for those who are interested in this ICT formulation, you can check our reference. So there's actually ICT formulation to get the optimal perspective relaxation, and there is use the ICT formulation programming to get the relaxation. And for the rank 1 relaxation by Gomez, it's actually if we use the same ICT formulation idea, then it actually becomes a bunch of others additional constraints on the SPT programming problem. And our convex relaxation can also be translated into this SPT simulation framework, and it becomes a bunch of new others SPT constraints, and which I write it down in this slide. And from this we can see that we can actually combine different constraints and to see that if we get a significant improvement. Yes.
It's time to wrap up. You've spoken for 25 minutes, Linchuan.
Oh yeah, I'm going to finish. Yeah. So yeah, we compare with this kind of existing method, and then we can show that our methods, although it actually add a different set of constraints, it only result in a very slight increase in solution time. And actually, by using our method with one of the others, we get the best optimal gap. And in some instance, just by simply using our relaxation, we get significant improvement for all the others relaxation. And I guess if I summarize our work, is that we want to solve the structural regression problem using the mixed integer technique, and also we provide a general framework that can strengthen the reformulation of this mixed integer problem by using the perspective idea. And we consider arbitrary constraint and arbitrary convex objective. Okay, that's my presentation.
Very good, very nice, Linchuan. We have time for a couple of questions. Well, let me mention one. You stated that the unit commitment problem is one that you can convexify.
So in unit commitment problem, there is also a track structure of using this indicator variable where we model the active time of our generators. And in some if we look at the particular unit commitment formulation, so there is a particular term that has a similar like on and off relationship. In that sense, we can use our classification result.
I see. Very good. Well, congratulations again to you and to Simge, your supervisor, for bringing this nice work here to fruition. And now we're going to move on to Yufeng.
Sure. Okay, let me share my screen. Okay, so
Yep.
So it's my honor to talk about our paper, Can Temporal Difference and Q Learning Representation in field theory. Thank the committee member for awarding me such a prize. This is a joint work with Qi Cai, Zhuoran Yang, Yongxin Chen, and Zhao Wang. Many thanks for their help. Recent years, deep reinforcement learning has achieved phenomenal empirical success, especially in challenging applications where the agent acts upon rich observations, such as images and texts. Examples include video gaming, robotics, and autonomous driving. The empirical success are empowered by the representation learning, which uses neural networks to learn data-dependent feature representation. However, the theoretical understanding of deep reinforcement learning is rather limited, especially how the feature representation evolves during the training process. In this talk, we studied two of the most famous algorithms in deep reinforcement learning, temporal difference learning and Q learning with neural networks. We aim to characterize the optimality and convergence of these algorithms. Let's start from some background knowledge on reinforcement learning. In reinforcement learning, we have an agent interacting with the environment. At the state ST, the agent takes an action AT, then the environment gives the agent a reward RST-AT, and then transits to the next state ST+1. The goal of reinforcement learning is to maximize the expected total return. So we consider a Markov decision process composed of some tempo of S, A, P, R, and gamma. Here, S is the action space, S is the state space, A is the action space, P is the transition kernel, R is the reward, and gamma is the discount factor. We see P is a transition kernel as the environment transits to the next state as prime according to P for given state S and action A. We consider the agent chooses its action based on a Markov policy pi. Also, we define the Q function QSA, which is the expected total return given the initial state and action for following a policy pi. In this paper, we consider the function approximation to be a two-layer neural network. Here, sigma is a smooth function and alpha is a scaling parameter. For example, we can consider sigma as a two-layer neural network with the sigma function as its activation function. We consider such a form of neural networks that is taking sum over I and give a m 1 over m because we want to utilize its invariance with respect to the permutations of these cities. We consider two questions in RL. The first is policy evaluation, which aims to estimate the Q function via the function approximation. The second problem is a policy improvement, which aims to find a policy that maximizes the expected total return.
Just a clarification question here,
Sure.
Yufeng. I suppose that if your neural network has more than 2 layers, nobody can prove much. Is that correct?
Yeah, and now we are consider the two-layer neural network, but for deeper, we don't know how to prove them.
All right, great, sure. Go ahead, thanks.
Okay. So I start from temporal-difference learning or TD learning. TD is an algorithm that solves policy evaluation problem by minimizing the mean squared projected Bellman error, or MSPBE. The global minimizer of such an objective is the best estimation of Q function in a function class F. Here, T pi is a Bellman operator, F is a function class, and D pi is a stationary distribution induced by pi over the Markov decision process. Given such an objective, TD updates the parameter along the direction of stochastic semi-gradient of MSPBE. We see that the semi-gradient is a first estimate of the gradient of MSPBE. Thus, challenges arise. First, there is a bias. There is a bias in the semi-gradient, and the function approximation is nonlinear in the parameter. Thus, this together can causes the temporal difference learning to diverge. And previous analysis considers fixed feature representation and essentially consider the linear function approximation or linearized neural networks. They fail to characterize the evolution of the feature representation, which is an important part in the empirical success of deep reinforcement learning. To handle such a problem, we consider the mean field limit of the TD updates. In particular, we consider the infinite width limit of the neural network for theta I drawn from a distribution rho. The function class is generated by such a representation form. Note that we consider an over-representation regime. That is, we represent the function class F by a larger function class alpha F for some alpha that is much bigger than 1. The function class can be represented by the neural network is much larger than the function class we are considering. So due to the universal function approximation theorem, such a function class captures a large amount of functions. We remark that such a limit form of the neural network factors the invariance of the neural network with respect to permutations of the parameters. We also consider the continuous time and infinite width limit of TD. We show that the limit of TD can be approximated by the solution to a limiting PDE. We can use such a PDE as modeling the parameters of TD via a particle system. There is a rich mathematical literature on this PDE, which is motivated by the study of interacting particle systems in mathematical physics. In particular, rho can be viewed as the density of a particle system, where g is the velocity field of the system. We can view the solution to the PDE as a gradient flow in the Wasserstein space. So we show that the approximation of TD by the limiting PDE, we establish a proposition on such approximation. We show that TD can be viewed as a discretization of the limiting PDE. And as the step size epsilon goes to 0 and the width m goes to infinity, the empirical distribution of the TD parameters weakly converges to the solution of the limiting PDE. We present the proof sketch of the approximation of TD by the limiting PDE. We consider some intermediate dynamics to help the analysis. We first approximate TD by its population version, the expected TD. This approximation can be proved by concentration inequalities. Then we approximate expected TD by its continuous time counterpart. This approximation can be proved by the discretization in terms of the time. Third, we approximate continuous time TD by the ideal particle corresponding to the limiting PDE. We see that the difference of ideal particle and the continuous time TD comes from the updating direction. In ideal particle systems, we consider the infinite width neural network in the update direction, while continuous time TD uses the finite width neural networks. Finally, we approximate the ideal particle by the limiting PDE. There is a known result that there is a correspondence of the limiting PDE and the ideal particle. That is, the density of the ideal particle systems is the solution to the limiting PDE. Then, after we show the approximation of TD by the limiting PDE, we establish the theorem on the global convergence of the limiting PDE. We show that with some assumptions, the neural network converges to the global minimizer of MSPBE. The error is 1 over p plus 1 over alpha. The assumptions needed are not restrictive. That is, we assume that the state action pair lie in a unit ball, and that the function sigma is bounded and smooth. As we can see, the scaling parameter alpha leads to a trade-off between the error of TD and the representation learning. That is, a larger alpha leads to a smaller estimation error, while a smaller alpha leads to a more deviated and powerful feature representation. The key technique of our analysis is the first variation formula in the Wasserstein space. Here, rho t is a solution to the limiting PDE. Rho star is the best estimate of the MSPBE parameter. And V is the direction of the geodesic connecting rho t and rho star. And G is the evolution direction of the limiting PDE. We measure the distance between rho t and rho star by the Wasserstein 2 distance, which is induced in the study of optimal transport. The Wasserstein distance can be viewed as the minimal cost for transporting some particles with density rho t to density rho star. The first variation formula can be viewed as a generalization of the first variation formula in the Euclidean space, which serves as an important tool in convex optimization. Accomplished with such a formula, we see that Wasserstein space can be viewed as an infinite dimensional Riemannian manifold. Then we apply the first variation formula and get such an equality. The next step is to upper bound them separately. For the first time, we establish a notion of the one-point monotonicity in the Wasserstein space, which connects to the first time to the optimization gap. Here, beta t is a geodesic connecting rho t and rho star. For the second term, by the overrepresentation parameter alpha, we show that the second term is upper bounded by 1 over alpha. Then plug in the above two inequalities into the first variation formula. We show a differential form of the upper bound on the optimality gap. Finally, taking integration on both sides and rearranging the terms, we complete the proof of our main results. So recall that we prove the approximation of TD by the limiting PDE. Thus, combining the convergence of the limiting PDE and the approximation result, we derive the global convergence of TD. We see that TD converges at the rate of 1/t plus 1/alpha up to some discretization error delta. Specifically, delta converges to 0 as the weight of the neural network goes to infinity and the step size of TD goes to 0. So now we finish our presentation about the convergence of TD. We then move to the Q-learning. Q-learning solves the policy improvement problem, that is, maximizes the expected total return for a given initial state distribution. We consider Q-learning and its variants soft Q-learning for such a problem. In Q-learning and soft Q-learning, we update the parameter via the stochastic semi-gradient descent, where the target function is the maximum of the soft max or the maximum of the Q function with respect to the action. We denote by the Q diamond of the maximum or the soft maximum of Q with respect to action A. So similar to the analysis of TD, we show that Q-learning can also be approximated by the solution to a limiting PDE. With an additional assumption on the regularity of the function class, we establish the global convergence of Q-learning and soft Q-learning. The proof is a generalization of that of TD. So that's it. Thank you for listening. Please let me know if you have any questions.
Very nice. Okay, good. Yufeng. Yeah, we do have time for questions.
Okay.
So let me see if I understand your temporal difference result correctly, right? You're using convergence of the PDE in order to prove convergence of the discrete process. Fine.
Yeah.
Now, do you have to assume that the neural network has infinite width in this result?
For the convergence of PDE, we need to assume the infinite width neural network, but we do show the approximation of TD by the finite width neural networks. We see that this is a finite width. This is a parameter in the finite width neural network.
Right. Okay. And in your main result, there's a minimum, and k has to be less than t. So you select. Actually, you can bring your main result for the temporal. No, the next one.
Yes.
Your final result.
Yeah, here is it.
No, can you go a few more slides?
Oh, I see. So you mean the convergence of TD?
That one, yeah. So k is less than t over epsilon.
Yeah. So actually, it's like when epsilon goes to 0, such a process is really long.
Yeah. So you're going to hit eventually, it's not monotonic or anything, but the distance eventually, if you pick up one of the k's,
yeah,
very long process, you get that behavior 1/t.
Yeah.
1/alpha. Very good. Okay. Oh yeah, that clarifies what my question. Let's see if there's any other question. Well, I don't know if Professor Nemhauser is still there.
I'm here, yeah.
Let's take a minute just to chat a little bit with you, George.
Yes.
So you are very well known to our students. Everybody
Good.
knows your books, everybody knows your work, and everybody knows about the work that you did at Georgia Tech. There's a double contributions that you made to the community. So for our students, it's an honor to have your name in the prize. And I think it's an incentive to keep the quality high.
Thank you, Jorge. It's very nice of you to say that. And I'm so glad that the department at Northwestern, which was, you know, I was part of the first group of PhD students at Northwestern, one of the first 3 PhD graduates. I think the other 2 graduated with me are no longer with us. Mike Shetty was one, and another one was Chuck Beetler. Leo Wilner, remember him, he followed just a little bit afterwards. And so did Eric DiNardo. Jack Mitten was just a great professor who I think motivated us all in getting involved in this new subject called operations research, which nobody had heard of. And my parents had told me that I was absolutely insane to move from chemical engineering to this crazy field that involved computers, and wasn't clear that computers were going to be staying with us anyway. So, but I took my chances and I've been quite happy since then, and so glad to see the unbelievable progress that Northwestern has made in the department in recent years. Great new hires.
And the building was the same, right? It was the same tech building, but just
Same tech building, yes. I think it's been expanded since then, but it was a fairly new building then, yeah.
Mm-hmm. Very good. Good to hear that. Thanks everybody for coming here. Enjoy the prize winners. Have a good day, George.
Thank
Bye-bye.
you. You all too. Bye-bye.